This video is an example on how to use XFLR5 software for evaluation of aerodynamic and stability characteristics of an unmanned aerial vehicle. We will use the Skyhunter 1.8 meters wingspan long-range UAV for exemplification. XFLR5 is an analysis tool for airfoils, wings, and planes operating at low Reynolds numbers. It includes X-foils direct and inverse analysis capabilities, wing design and analysis capabilities based on the lifting line theory, the vortex lattice method, and on a 3D panel method. XFLR5 is open software and can be found at www.xflr5.tech. We will start by creating a new project and opening the coordinates file for the airfoil of the main wing, the Clark Y smoothed airfoil. In the Pressure Distribution tab, Op Point View, we can see the shape of the airfoil and its main characteristics, such as maximum camber and thickness. Next, we will refine globally the airfoil to 200 panels, for better convergence. Then, add trailing edge flap deflection of -5 degrees with X hinge at 71% of the chord and Y hinge at 50% and save as new airfoil. We do the same again, but for +5 degrees deflection. These will be needed to study lateral directional characteristics for steady movements where aileron deflection is different from zero, like the coordinated turn. Next step is to add the airfoil for the horizontal and vertical tail, the NACA 0010. We will add the -5 degrees trailing edge flap deflected airfoil also. When applied to the horizontal tail, it will be used for longitudinal trim and stability study. Now we can evaluate the aerodynamic characteristics of chosen airfoils in a multi-threaded batch analysis for a chosen range of Reynolds numbers between 50,000 and 660,000 and a given range of attack angles. When the analysis is ready, we get aerodynamic coefficients for lift versus drag polar, lift versus angle of attack, pitch moment versus angle of attack and wing efficiency versus angle of attack. Remove non-converged and inconvenient polar or polar data points, save the file and open wing and plane design. Start defining the wing by entering the wing geometry by segments length, chords, offset and dihedral, followed by the section's airfoil and desired number of panels in X and Y directions. Add small span sections of no more than 5 mm for the gaps of command surfaces as ailerons and flaps. Then, add the inertia information as wing structure mass and all other concentrated masses on the wing, servos, pylons, engines, and nacelles. The program will compute inertia moments with respect to the chosen origin and to the center of mass. For flaps definition, we must use the flap deflected airfoils defined before. We change the airfoil only for the affected span and leave the neighboring gap section airfoil unchanged as seen here. For lateral directional movements computations, aileron can be added using flap deflected airfoils. In this case we must define a non-symmetrical wing and select different airfoils for the left and right side. Now, one can see more clearly the necessity of the gap sections. Aerodynamic characteristics of the wing can now be analyzed. We chose a sequence of attack angles between -5 to 10 degrees and run the analysis. For some angles of attack and Reynolds number we may get interpolation errors. We can go back and add more Reynolds number polars for the airfoils or ignore and delete the corresponding point of the obtained polar. Next, the fuselage geometry is to be added using stations along the x-axis. Each station can be defined by minimum 5 points in the right side of the xz plane. The fuselage is assumed to be symmetrical. Number of panels is selectable and smoothing Bezier curves of chosen order are used to define the outer shell of the fuselage. The number of points defining a section can be increased by inserting more points, but all sections must have the same number of points. As for the wing, the masses can be added for the inertia computations. Aerodynamic characteristics of the wing fuselage combinations are determined in the same manner as for the wing. The next step is to add tail. We start with the horizontal tail. It is defined in the same manner as the wing was. We choose the NACA 0010-5 degrees as the airfoil in order to be capable, later, to do advanced stability analysis, which requires variable deflections of the elevator. Do not forget to add inertia information too. Then we do the same things for the vertical tail. Observe the check mark for the double fin. Finally, we have the whole plane ready for the study. We do a simple analysis for determining the right range for the center of gravity at the cruise speed. This is done by observing the pitch moment coefficient versus angle of attack. For longitudinal static stability, it is required the slope of its graph should be negative. The angle of attack for which it is 0 is the equilibrium point in steady horizontal flight. We continue with the advanced stability analysis. Here we use the plane inertia data entered before. We specify the control by entering a gain of 1 for the two sides of the elevator, the deflected part of the horizontal tail. That is why we needed deflected flap airfoils. Viscous drag is not taken into consideration in these computations, so we must add the zero drag manually. To start the analysis, we chose a sequence for the control parameter, keeping in mind the initial deflection of -5 degrees. So, a range of the control parameter of -10 to 10 means deflection of the elevator of -15 to +5 degrees. In the log window we see for each value of the control parameter the elevator deflection, the steady state horizontal flight angle of attack and speed, inertia moments, stability and control derivatives and matrices, characteristic polynomial roots. At the end of the analysis we can plot the root locus graph to check the dynamic stability for all longitudinal and lateral directional modes, that can be identified by the roots. Animation of the relative movement with respect to the center of gravity can be shown. We observe that the longitudinal short period and phagoid modes are convergent and the lateral directional roll and Dutch roll modes are convergent too. The spiral mode is slightly divergent, but the doubling time is large enough to be acceptable. Non-convergent points can be eliminated from the analysis and, we can add computation points in the desired zone. This conclude our presentation. Hope you liked it. See you next time.